In this discussion video, we'll do a problem where we find the volume of a sphere using integrals. So this is problem number 8 from worksheet 15, and we want to do just that, find the volume of a sphere of radius little r using calculus. So little r here is some constant, some fixed number. So before I give you a chance to try it, let's draw a picture. So I'm going to draw a sphere. So we have the circular shape, and to make it look 3D, maybe I'll put some lines like this. So it's a sphere here. And just to get you started, I'm also going to draw some axes. And I think the most natural way to draw the axes would be so that the center, the origin, is at the center of the circle. And I'll draw the x-axis like this, and the y-axis like this. So here's my x-axis, here's my y-axis. And now I want to give you a chance to try it. Pause the video for 4 minutes and see if you can carry it on from here. 4, 3, 2, 1. Pause the video for 4 minutes and try this question. All right, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about it. So the next thing I need to do is I need to form some cross sections. So I can either slice this sort of horizontally, perpendicular to the y-axis, or I can slice it vertically, perpendicular to the x-axis. And for this question, it doesn't really matter because the slices are going to look the same either way. So maybe I'll slice it perpendicular to the x-axis or parallel to the y-axis. So if I do that, a point like this, so the slice would look something like, it would be a circular. It would be a circular slice, cross-section. And that cross-section has a little bit of thickness, tiny bit of thickness, which I'll draw in the x direction. Okay, and I'm going to call this dx, because this dx is getting really, really, really small. And as it gets infinitely small, that cross-section, and if we add up the areas of an infinite number of cross-sections like this, it would perfectly give me the volume of this whole shape. And you know what? I can't remember if I said add up areas of cross-sections or volumes of cross-sections. We're going to be adding up volumes of a bunch of slices like this. And that is going to give me the volume of the whole thing as I let that dx get closer and closer to 0. So at this point, let's recall our formula for volume. It's going to be an integral, and it's going to be a dx integral, because the direction of the thickness here is in the x direction. All right, and that means when I write my area of my cross-section, I will write it as a function of x. Okay, so looking at my picture, this is a circle of radius r, so that means this is r on the x-axis, this is negative r on the x-axis. Okay, and this would be positive r on the y-axis and negative r on the y-axis. So the smallest x gets is negative r, the biggest it gets is positive r. All right, based on the symmetry of this picture, by the symmetry, I can simplify it a little bit. This will be equal to, I could just do the integral from 0 to r of my cross-section area dx, but then double it. So by symmetry, I could just find the area of half of this region and then double it. This is going to be a little bit nicer computationally just because it's easier to plug 0 into something than it will be to plug in negative r. But if you wanted to keep it negative r to positive r, there's nothing wrong with that. Okay, so what is the formula for the area of these cross-sections? Okay, so we'll get 2 integral from 0 to r. So my cross-section is a circle. So let me draw the radius. I'm going to call it big R because I already have a little r in the problem. Okay, so the area of the cross-section is going to be pi. It'll be pi big R squared dx. Okay, so we need to know what big R is in terms of the variable x. So to get that, this point, it's sort of determined by that point. If I call this point x comma y, notice that that top point is on this circle. It is on this circle centered at the origin with the radius r. So the equation of the circle, just the circle, not the whole sphere, would be x squared plus y squared equals the radius squared, which is little r squared, that's what we'll get. And to find big R, I need to know the y coordinate. So I'm going to isolate y, and we'll get y equals r squared minus x squared being square rooted. Typically when I square root both sides, I gotta put a plus or minus. But at the point that we chose, the y value at that point is non-negative at the one that we drew. So we don't need the plus or minus. We will just take the positive root. All right, so if I plug in, we'll get 2 times the integral from 0 to r. And we'll get pi r squared. So r is little r squared minus x squared being square rooted. Then I got to square that. All right, so I can pull out the pi, and we'll get 2 times pi times the integral from 0 to little r. When I square this, the root goes away, and I get little r squared minus x squared dx. All right, so now we're almost there. We get 2 pi times r squared is just a constant, because r is a constant. Little r is a constant. So its antiderivative will just be r squared times x. And then minus, I'll get x to the third over 3 for that next antiderivative. Then I got to plug in the 0 and the little r. So we'll get 2 pi times, if I plug in little r, we'll get r cubed. And in the next term, we'll get r cubed over 3. And then we'll get minus, if I plug 0 into both of those terms, we'll get 0. So 0 minus 0. And simplifying, this becomes 2 pi. And in the bracket, we get 2r to the third over 3. And if I multiply this out, I get 4/3 pi little r cubed. And you might recognize that as the formula for the volume of a sphere. We've just proven where this comes from using calculus.